Okay, folks, we're back with part B of video for week 13. Going to be doing exercise 9.103 that you can find on page 389. We're looking at stock mutual funds and how they work. If you have, let's say, $10,000 to invest, rather than putting it in the bank and earning virtually nothing in interest, you could put it into a stock mutual fund. The mutual fund company would take your money and money from other investors and buy stocks, shares of stocks that they think are going to increase, pay dividends, make you rich. Now, the catch is, of course, sometimes they make you rich, sometimes they make you broke. The last couple of years it's pretty grim out there. So if you invested that $10,000, maybe in 5 years it'll be worth $20,000. It'll double. Maybe it'll drop in half and be worth only $5,000. You never know for sure. Now, the mutual fund company, though, says, don't trust us, we'll take care of you. And, oh, by the way, we're going to charge you 1.19%, a little better than 1% of your money that you have invested will be paid to us to feed our families, to buy the Lexus we've always wanted, to go on that really great trip, all the things that stockbrokers like to do. Now, 1.19% of your $10,000 is what? $119 a year that they're going to charge you as a fee for managing your $10,000. It's therefore in your best interest to pick companies that have low investment ratios. Companies like Vanguard like to advertise that they have ratios of 0.1 and 0.2%. But the other companies will say, well, that's fine for Vanguard, but we do a better job than they do in picking stocks to buy. You can make your own decision on that one. Nonetheless, what the question here is whether that 1.19% ratio, which was true 10 years ago, is still true today. To answer that question, someone went out and did a survey of 12 stock mutual funds and found that the average was 1.63%. The average expense ratio had gone up, apparently, to 1.63%. So the hypothesis question is the 1.19% ratio still valid? Is it dropped, in fact, below that value? That's our null hypothesis. Or if you can't believe that, we must conclude then that the new expense ratio is something greater than 1.19%. Now, 1.68, again, is greater than 1.19, so the knee-jerk reaction is to say, oh, sure it is. It must have gone up. But we have to look at the standard deviation. Now, we don't know the population standard deviation. All we've been told, really, is that the distribution is normally distributed. The shape is normal. And if you look at page 386, our little decision tree here, we can go through that real quick. First of all, we don't know the value of sigma. We only have the sample standard deviation, so we don't know the population standard deviation. So we have to take the no branch. Is the population normal? Well, we're told it is, so that means we can drop right down and use the t statistic. But what if we didn't know that? And what if we weren't even sure that it was mound-shaped or not very skewed? Well, then we'd have to make sure that our sample was large, at least 30. So in this case, where we only have a sample of 12, we'd be out of luck, and we wouldn't be able to conclude this analysis. But because we know it's normal, then we can use the t distribution. Okay. Now, what we're going to do with the critical value test that we're asked to perform is to establish some benchmarks, some points where we think that we can believe the null hypothesis or we can't believe it. Remember, here's the experiment. If the true value of the population is still 1.19%, the question is, what are the odds of picking a sample of 12 stocks and have that come out to be 1.63%? Can we believe that we're so unlucky as to have it come out that much greater than the historical mean, than the null, than the status quo amount of 1.19%? If this is just too impossible to believe, we've got to reject H0 and accept HA and assume and conclude that the average is something greater than the old historical average of 1.19%. So the question is, how far to the right of the standard deviation is 1.63? And we'll answer that question in a moment. But first we have to set the benchmarks. How far out are we going to allow ourselves to go and still believe the null hypothesis? Well, we do that by coming up with some critical values. Now we could go to the table at the back of the book and look these numbers up. We would search through the table for the number of degrees of freedom we have. In this case, 12 minus 1 is 11 degrees of freedom, and go across until we find 0.1. This is a single-tailed problem because we're dealing with a greater than problem. And we could find 0.1 in the table, and that will give us a critical value. Rather than do that, I'm going to use T inverse, which asks me for the probability and the number of degrees of freedom that I'm interested in. And that says it's really 1.8. So that saves me going back to the back of the book and finding that value. And I can drag this, whoops, I forgot to put my dollar sign in. And I put a dollar sign in front of B4, so it keeps on being B4 as I drag across. And that says, depending on how certain we want to be, we need a critical value of 1.8 to 4.4. So if we look at their little picture again, 1.8 would be somewhere in here, just shy of 2, and 4.4 would be way out here. So depending on how certain we want to be, our test statistic, the sample that we took, this 1.63, has got to be no more than 1.8, 2.2, 3.11, or 4.44, again, depending on how certain we want to be. Okay, what is the test statistic? Well, it's the number of standard deviations that the sample mean is from the assumed mean. So the difference is the 1.63%, whoops, forgot the equal sign, 1.63 minus 1.19, but I have to, that gives me a number that's 0.44%, but I really don't want percentages. Incidentally, don't get fooled by the percentages here. These are just numbers. They're not proportion problems. This is not a proportion problem. These just happen to be numbers that are expressed as percentages. I'm interested in how far 0.44 percentage points is from the mean, how many standard deviations that is from the mean. So I have to divide that by the sample standard deviation, which in turn has to be divided by the square root of n. And I think I need another parentheses. There we go. Whoops, I don't want a percentage, I want a real number. So I'll just click on that. And it's 4.92. Well, we can see that 4.92 is greater than any of our critical values. So there's no way in the world we can accept the null hypothesis. It's just too incredible to believe that we would end up with a sample average value of 1.63% when the historical average is 1.19%. Something's wrong. Either we're just incredibly unlucky, or the conclusion we must reach is that the null hypothesis is wrong. And if the null hypothesis is wrong, we have to accept the alternative hypothesis. Incidentally, if we wanted to do this as a p-value approach, we could say, what is the percentage associated with 4.92? Well, we could do that by looking in the table again, but you know me, t distribution of x, which is 4.92, and the number of degrees of freedom, which is 12 minus 1, and the number of tails we want. We only want one tail because that's all we need. And we get a value of 0.00023. And again, 0.00023 is much less than any of these values. So again, using the p-value test, we have to reject H0 and accept HA. Okay, that's it for this time. Ask questions. This is review week. Use the discussion. Use I don't get it. Make sure your questions are answered so you do well on quiz 3. Thanks for listening. We'll see you next time.